on this topic. So today we're having a very nice talk on decentralized deep neural networks architectures and how these architectures are having some limits by working separately, how they could be brought together to learn in a better way, which is having lots of implications for distributed computing and edge computing. And we will learn about the teaching and student paradigm in order to learn better how the learning can be done there. So I encourage you all to really follow all the presentation till the end. In the case you're having any questions, please write your questions in the chat, and then at the end we will present your questions to Professor Pitas. Also, if you want to intervene at the end vocally, orally here in the meeting, and that's perfectly okay. We do it at the end again. So we now proceed. We are having something like, let's say, 45 minutes and 15 minutes of discussion, debate, and questions and answers, maybe. Well, this is all. I let you in the very good hands of Professor Pitas for this presentation. Thanks for the presentation.
Okay, thank you very much, Enrique, for your introduction. Ladies and gentlemen, nowadays there is a big discussion about decentralized architectures, about having intelligent agents that talk to each other and they conspire on how to destroy the human race. So it's high time to have a scientific discussion on these things, because besides the hype, there is also scientific research, and that's what I'll try to do today in this lecture. So we're going to discuss about decentralized DNN architectures, how we train them, how we test them, and I'm going to present you a few applications on visual data analysis. However, the same ideas can be applied to almost any application of machine learning and computer vision and so on. So I'm going to describe first what's the decentralized DNN architectures, and then how we can employ them for visual data analysis. In decentralized deep neural network architectures, we have many DNN agents that distribute the computation and decision-making across multiple DNN nodes, and this way we have scalability, privacy, because the data don't move away from their owners and producers, and of course we have robustness. So the first, when we talk about decentralized DNN architectures, we have distribution of data and computations across multiple nodes. That's a good thing to do, because we distribute the computational memory needs across various devices in the world, in the cloud, for example. Then the nodes can cooperate with each other, either for training or for inference. We have privacy preservation because the data remain local. We don't necessarily move data around and far away from their original owners. And of course, we have fault tolerance, because if we have decentralized architectures, we don't have a unique node of reference, and this means that we have tolerance. If some of the nodes don't operate well or malicious, we can recover from such problems. So we can have peer-to-peer networks. In this case, we have collaborative machine learning. This means either training among peers or also testing and inference, again, among peers. And of course, we can deploy these DNN agents either on the cloud or on the edge. In some cases, where for example, when we have drone vision and we have the production of lots of data on drones, for example, videos, it's not a good idea to transfer those videos far away into the cloud, because this creates a tremendous communication overhead. It's best to do edge computing in these particular cases, and then communicate the results of DNN training or inference to other nodes, rather than sending around raw data. So when it comes to peer-to-peer DNN computer, we have decentralization, because we have reduced dependency on central servers. This means that we have better scalability and robustness. Of course, we have resource efficiency. in the sense that local computing resources, whether GPU resources or memory, they are best taken care of and used. If we have node failures or if we have attacks, then we have certain robustness and resilience in those cases. And of course, we have community driven innovation in the sense that we can transfer knowledge among the various DNN nodes, as you're going to see. When it comes to DNN computing, it's very important in certain application areas, particularly in computer vision, because in computer vision we have images and videos, and we cannot move them around in the cloud because this creates communication of big communication overhead. So we prefer to have local edge computing. Which means that we have low latency because we process our data immediately at the edge. We don't communicate lots of information around, and this means that we have bandwidth efficiency. The data stay at edge devices. So this means that we have privacy preservation. And if some nodes are disconnected, the rest of the nodes can continue operating, and then we can have local connectivity computing as well. I'm going to show you a general architecture that can be used in such cases for DNN training and inference. And I can just present you an example that's related to knowledge distillation. In these cases, we have a trained teacher model. It's a DNN model that can be a fairly big one and well trained. And then we have a smaller DNN student model, and we try to train it by learning not only from local data, but also from a teacher model. And within this framework, we can support teacher-student DNN architectures, as you are going to see. And in the case of knowledge distillation in particular, the student DNN tries to mimic the teacher DNN output by combining both local information, local training data, for example, and also teacher DNN model predictions or intermediate features. And to this end, we use particular objective loss functions to be optimized that take into account not only performance on local data, but also the discrepancy between the student DNN predictions and the teacher DNN ones. So essentially, in cases where we use this length framework, we try to mimic what happens with humans. In the case of humans, in class, we have one student or multiple students. Typically, we have one teacher, and then we have some external trigger for example, a new quiz, and then the student tries to mimic what the teacher knows. So essentially, that's the type of interaction between students and teachers that we try to mimic within the LANC framework. And to this end, we have various DNN nodes that can be either student or teacher ones. The student tries to find the best possible teacher or multiple teachers, and then tries to get knowledge from the teacher nodes. Let's suppose, for example, that we have n capital length nodes, and we define a length class that has at least one teacher and multiple student nodes. In the length framework, we can also support multiple teachers and multiple students as well, and the students can choose their teacher that knows best the specific task. Teachers, by the way, teacher DNNs may learn as well, because sometimes teachers can learn from student notes. And this means that we can interchange teacher and student roles on certain machine learning tasks. And we can use length framework either for classification tasks where we have a number of semantic classes and we want to make inference. For example, in the case of natural disasters, we have images that show wildfires or floods, and we have to classify an image that it belongs to the wildfire class or to the smoke class or to the flood class and so on. Or we can have regression or clustering tasks. For example, when we do object detection, then we have to solve both a classification problem to find the car, for example, and also we have to solve a regression problem in the sense that we have to find the bounding box that includes the image of a car. And students can cooperate with each other during learning. Teachers can pull together their knowledge, especially if they don't know well a particular task. And typical length nodes have cooperating behavior. But we can also envisage cases where we have competing behavior between the length nodes, because, for example, some length nodes may be ignorant for a particular task and yet they participate into inference, or even worse, they can be malicious. When it comes to length node architecture, essentially the length node is a DNN where we have a feature module that creates features out of an image. And then we have decision heads, one decision head per task. And of course, we can train the feature module and the decision heads on certain data. But then the problem is, can we somehow assess what a length node knows? We can do this by incorporating another module, which we call it knowledge self-assessment, that can be used to decide whether for example, a length node has seen car images, or whether it has seen flood images, or whether it has seen both smoke and fire images, and so on. And length nodes should interact with each other, and this means that we need an interaction manager. When it comes to the feature module, essentially it's the backbone of a DNN where the feature modules that we produce can be shared among various tasks. We have the feature extraction module has a certain structure. It can be parameterized by its DNN weights. Now, when it comes to knowledge self-assessment module, this module does the following. Let's suppose that we have a data set D that is being used to train a length node. Then we can devise an out-of-distribution detector, and if we have a new image, X, we can check whether this image is within or without or outside the training dataset for this particular module. So essentially, we use an out-of-distribution detector to understand whether a length node has been trained with car images or with person images and so on. And if the knowledge assessment module detects more than one decision heads that are relevant to the particular task that we have, then we can choose the one that has best performance for this particular type of data that we're interested in, or we can use more than one of them. So when it comes to the decision heads, they operate on the outputs of the feature module. We can have a number of them, one per task, and essentially we can concatenate the feature extraction and the decision head to reach the decision. And the interaction manager does the internode communications. For example, it can exchange data, or it can exchange weights, or it can exchange image features or logics of the various length nodes. So the main function of the interaction manager is the following one. Let's suppose that we have a node that receives data from its environment, and this data is about, for example, car images, and it doesn't know about car images itself, so it sends a subset of these images to other nodes and receives their responses, and based on the responses, it can understand whether other link nodes can serve as teachers or as fellow nodes for decision making, for inference. Now we have a number of policies that we support in this framework on what we receive from another node. For example, we can receive the average classification accuracy on a particular car data set, car image data set that we send to the various length nodes to understand if they know a task or not. The car classification task, for example, or we can use to descend the out of distribution detector score, or we can use a disagreement between the current link node and other link nodes. So we have a number of policies that to exchange information to be used for teacher selection. And once we exchange information, between a current node and other nodes that possibly know a certain task, then at the end, based on the output that we receive from these nodes, we can decide whether we have one or multiple possible teacher nodes. If it's only one, then we try to learn from this teacher node. If it's more than one, then we can either choose the best, or we can try to learn from multiple teachers. This is doable as well. Now, let's suppose that we have identified one teacher length node, and we have the length student node that has to learn from the teacher node. Then we have a number of options that to exchange data between the two and let the student node learn from a teacher node. For example, first of all, we have option number one, which is training data transmission. If the student node does not know about car images, then it can receive a number of car images from a teacher node and then to retrain. This is one option. Another option is once the teacher node is identified, then we take its soft output activations for a number of images, and we send them to the student node, and we use this extra information for local student length node training. Another option is to send image data to a teacher node, and then we receive both the soft output activations and the image features from teacher nodes. And then we use these two sources of information to perform local student training. And of course, the last thing is that we can receive from the teacher node the entire set of weights that describe the structure of the teacher node, and then we can reuse them without extra data in the student node. So we can use any of these approaches for doing student node training. Now, where we can use these things? We can use them for classification. We can use them for regression, object detection, for example. We can use for image segmentation. I'm going to show you some results in the project that we have that we currently run, or natural disaster management. We can have object detection, which is a classification plus regression task. And we can have also clustering applications. So here, for example, you see wildfire images where we have tried to segment the fire or flame regions and the smoke regions, and we have done it fairly well. And you can do it you can do wildfire segmentation training in a teacher and student framework, as I've told you already. Here it's another application area that we encountered in the TEM project that funds this research. You see here we have flood images, and we try to do flood image segmentation. Again, we can use the length framework to teach local students to learn from other teacher notes. Let's suppose these images come from Germany, from the Ardal Valley, and let's suppose that the German authorities have a very good teacher DNN trained on flood image segmentation. And here in Greece, we also have such problems with floods. We have a student model here that is not that well trained. We can ask information from the teacher DNN node in Germany to learn about or to learn how to segment flood images. One way to learn is through federated learning. In this case, we have various nodes that are decentralized. They have local data. They are trained on those local data, and then they exchange information with the master node that does DNN model aggregation. Then, after this aggregation step, the data are resent to the teacher nodes, and we continue this process till we have derived a federated DNN model that runs well on all data without exchanging data among the various clients. This means that we have privacy preservation. And this way, we can through the proper DNN model aggregation, we can handle the cases where all the length nodes have identically distributed data about, for example, forest fires in pine woods. But also we can handle cases where the various length nodes have non-identical distributed data. For example, the Finnish DNN node on forest fire is about pine forest, but the forest fire segmentation node for the Mediterranean region, for Greece and Italy, they have been trained on other types of Mediterranean forests. And then when we do federated learning, we try to derive models that work well on both cases. In the case of peer-to-peer learning, the length nodes try to learn from each other, but they can help each other as well into doing distributed or decentralized inference. An important task is continuous learning. We can have a number of tasks, and we have models that solve one task, but then when we move from task 1 to task 2, then we don't really want to forget doing well task number 1, and so on. And there are techniques that support continuous learning, and this is supported within the length framework as well. We can have decentralized inference when we have a number of length nodes that do inference, and they cooperate with each other to do the best possible collective inference and get either one decision by consensus, or we can get multiple decisions. Each length node takes its own decision, but it does not use only its own inference capacity. It also incorporates inference information from other nodes. There are cases where we can apply the length framework for reproducing research results. If we have a DNN node that is a model in a published paper, then we want to replicate the model in the experiments, and we can do this using the length framework. I can show you some results of link framework experiments. For example, we have done collaborative knowledge distillation. In this case, we have used 4 link nodes that one of them has been pertained on a classification dataset on a number of datasets, for example, CIFAR-10. Each node, including the teacher node, takes the link student role exactly once after an education cycle, and we have multiple education cycles. And then regarding the data that we want to exchange, we take option number 2 that's referred to knowledge distillation, and then we observe what happens after 5 education cycles, and here are the results. We have compared it with a number of competing techniques, and our proposal has much better performance for knowledge distillation versus competitors. We have also proven that the length framework is the most tolerant architecture in the case we have small batch sizes, which is important for various real-world applications, because sometimes the student nodes have limited access to data. In the case of continual learning, we have 6 length nodes that we have tested them. For example, in the case of MNIST dataset, one node knows classes 0 and 1, second node knows classes 2 and 3, and so on. And we train a node in its own class, and then we retrain it on other classes. But this has to be done in such a way so that we don't forget previous knowledge. And to do this, we have done knowledge distillation, and we have added a specialized continual learning loss function to learn new tasks. And after 5 educational rounds, we see here that we don't really forget. Also here, we don't really forget the previous tasks. So we learn new tasks, but we don't forget the previous tasks. And we have done also work on federated learning. We had 1 master node as aggregator and 2 student length nodes to be trained on local data. The students have been trained for 50 epochs, and then they send their output to the aggregator. And we have done 4 federated learning rounds. Here you can see that after 2 rounds, we already converge. Also, all previous examples were about cooperative learning. Now I'm going to say a few things about decentralized and distributed DNN inference. Overall, we have either centralized DNN inference or distributed DNN inference, or decentralized DNN inference. They are different. For example, in the case of centralized DNN inference, all data computations are located in one node, and then we just take one decision. Of course, as you understand, if this node fails, then we have complete failure of a centralized system. Then we have distributed DNN inference, where we have length nodes that take inference that produce inference results locally. Then we collect all this information, and we take one decision for the entire system. Essentially, we do distribution of DNN inference in various clients, and then we collect all the inference results in one master, and then we take one decision. Again, of course, we have a problem that if this master node fails, then we have complete failure of the system. In the case of decentralized DNN inference, then DNN nodes exchange inference information, but each node takes decision for itself. Okay? This means that if we have n nodes, then we can have n different inference results, but these inference results are produced not only by using local information, but also by using information from other DNN nodes. And of course, in those cases, we have much better robustness, because even if some DNN nodes fail, then the others can continue operating. We have issues though, because in this case, we have different inference results for the same thing, produced by different DNN nodes in a decentralized way. And then there is a question whether we need consensus or not. In the case of aggregated operations, for example, if we use Fed averaging in the federated learning, or if we use majority voting, then in those cases we have problems, because if we have ignorant nodes, or if we have malicious nodes, then they can create problems both in federated learning, for example, and in majority vote. In those cases, it's better to use consensus-based techniques that are based on the Byzantine fault tolerance paradigm, to have a leg node consensus, and we have done this. We can address a number of attacks. For example, we can address malicious link nodes that try to manipulate the DNN model parameters and send false output decisions to other link nodes. Or we can address the Sybil attack, where an attacker tries to create multiple fake link nodes that can fool decision making and so on. And we have developed the so-called proof of quality inference consensus protocol to establish consensus among the various DNN clients for inference. The novelty is that we can have inference validation through BFT consensus, and we can have secure inference even under unreliable communications. And here you see that by using this protocol, we always have better results in the case when we have malicious nodes. In this particular case, we have from 1 to 3 malicious nodes. And if we use such consensus mechanisms, then we have full decentralization, we have privacy preservation, but we have certain issues regarding communication complexity that we have to address. Okay, it's fine to try to build consensus among the DNN networks, but if different DNNs know different things, then it's not a good idea to try to build consensus in this case. It is better to identify shards of DNNs that have domain similarity, have been trained in the same way, and then we try to have consensus in each shard independently. So, for example, here, if we have data samples and we have a number of shards, these of DNN agents that do more or less know the same task within a certain shard, then we try to identify the closest possible shard, and then we try to apply consensus within this shard. For example, here we have a number of nodes. Some of them are malicious, some of them are good ones. We try to identify a shard that knows about this task, and then we try to build consensus. In this particular case here, we have 2 good nodes and 1 malicious node, so at the end we get good results. And we have verified in simulations that if we have, for example, 15 link nodes and we have 3 link nodes that perform maliciously, our approach works well. On the other hand, if we use averaging or if we use majority voting, then they completely fail. Okay, how can we implement all these architectures? These are nice theoretical ideas, but we have to implement them somehow. And we have 2 different implementations. One uses Docker and Zookeeper. Each link node is physically located in one computer, and then Zookeeper tries to identify, to detect nodes and that are link nodes and receive their IP addresses for exchange of communication between the link nodes. Each link node occupies one Docker container, and as we Dockerize the link nodes, we can move them in the cloud fairly easily without bigger problem. The Zookeeper can discover other link nodes for cooperation and coordination. So here's how we Dockerize the various link nodes for exchanging information between them. Then we have Dockerized link training procedure and link inference procedure, where link nodes, as I've told you, try to identify potential teacher nodes. First of all, they try to identify other link nodes, then they try to identify other teacher DNN nodes for a particular task, and then they exchange information. For example, for federated learning or for decentralized inference. And here is the training process flow in the case of LANC architecture information exchanges. Now, I would like to present you another framework for LANC implementation. This is based on the Azure system, where each link node is an online endpoint, and communication between the link nodes is established via REST API. We have a ledger when each deployed link node writes the required information that can be accessed by other link nodes, and then we follow an event-triggered approach to operate the system. Essentially, each link node can produce two events. One OOD out. This means that this link node does not know about this particular type of data, or OOD in, which means that this data set is known to this particular link node. And then a user can trigger its link node with new task data. If the user node does not know about such data, then it sends through an event handler requests to other link nodes to check whether they produce the OOD in output event. And if they do so, then you can try to identify which is the appropriate teacher node, or we can use multiple teacher nodes as well. So here you see a user node that does not know about certain task data, so it produces an OOD output out. And then this triggers requests to other nodes to check if they know this particular data. Out of all these three DNN nodes, those here know about this particular type of data, so they produce an OOD in event, and this means that this is communicated to the user node. Use those two nodes as teacher nodes. And we have applied this for federated learning, as I told you already, on the Azure Cloud Platform, and it performs very well. We have also done continual learning on this Azure Platform implementation of the LANC architecture, and also we have done centralized DNN inference, same architecture. Well, This is maybe a good piece of science and a good piece of technology, what I've presented you so far. But what's the relation of what we do here with global AI market? So think about what's the current status of the global AI market. Few AI companies annotate data sets and they sell them. Many users and individuals produce massive non-annotated datasets. So this means that we produce private and corporate data that are typically non-annotated. We don't have any estimation of their commercial value, so we don't essentially know how much money our data are worth. And then what we do these days, the big companies, they just use such data that they find in the internet, and typically they don't pay a penny for them. So essentially, they steal those data. This is situation number one. Situation number two is the following one. There was an alleged case of Chinese companies trying to get information from open AI models. So essentially, they could manage to send requests to the OpenAI platform, get intermediate results, features, or outputs, and then they use them to train their own models. Whether this is true or not, that's another story, but that was an accusation. And it may well have happened. It may have happened. So, as you understand, it's not really a healthy global AI market because essentially we either steal data or we sell few annotated datasets or we steal intermediate results and outputs. And in some cases, there are companies that sell entire models. So, company that does forest fire detection, for example, can sell its entire DNN model. So this is another way to do business in the AI market. But can we put all these things in a unified framework? Essentially, data and DNN knowledge are a commodity. The problem is we know what data are, we don't know their value. Regarding DNN knowledge, we don't know exactly what it is. It can be the DNN weights, it can be the DNN output, it can be the DNN features. So we can use frameworks like Lang to exchange such information. As I've told you already, we can exchange data. We can exchange intermediate DNN knowledge. We can exchange final layer DNN knowledge, or we can exchange DNN knowledge. And this need not be done for free in the sense that if you implement a system like Lang at the international level, then information exchange can be done on a paying basis. If somebody wants to get knowledge in terms of data or in terms of final layer outputs, then this particular individual or company must pay for this knowledge. And this is doable. However, there's no such a system that implements the money flow in such an architecture these days. Because what I presented you here, it's a technical framework to exchange knowledge, but I didn't say anything on how to exchange money for to cover those information exchanges. And of course, all commercial data transactions must be taxed because nowadays we have big data or other types of commercial transactions among DNN companies, and they are not taxed, and this is not fair for us, the rest of the taxpayers. So that's all. if you want to learn a few things about these social aspects of AI, then I have written a book some time ago that was quite prophetic. At that time, for example, metaverse was the big thing to go ahead, and then I foresaw that it would fail, and it did fail. Example, at that time also, controlling social media access was not an issue, and I predicted that we cannot continue this way. And nowadays, Australia and other countries are thinking about banning the social media for minors. So this book is for the ones of you that want to have a bigger vision on what's AI and its impact on society these days. So thank you very much for your attention. I don't know if there are questions.
Thanks a lot. I was reminding all our audience to have questions in the chat. We don't have for the time being, but I would like to start making a question to you, Ioannis. You have been presenting a lot of techniques and architectures and ways of behaving with these agent systems. And I wonder what is happening with the real information that is traveling between nodes on the internet. Are you using any kind of cryptologic systems or key ways for protecting the information between nodes?
So this is a very important issue. I did not touch this aspect at all, but it's a very serious issue because if somebody poisons the communication channels, then you have a problem, and also you have to find ways to address malicious nodes. We have devised some techniques to this end, but more has to be done.
Yeah, and even just listening, they don't need to interact by
Sure,
acting.
definitely.
This information that is being used for training, this information could be subject to rules for not
Yeah,
disclosure.
because they get information for free this way.
Yeah, also, yeah. Interesting. Please, those who are in the audience, don't be shy and raise your hand, and we will be happy to have your questions. In the meantime, I would like to know more, Ioannis, about the settlements you were researching for federated learning. They were using real smartphones, Raspberry Pi, the type of nodes we have in federated learning.
So far, we did not experiment with different hardware devices. We have experimented with DNN nodes that reside on different cloud computers in the framework of demo project, for example. But this is something that has been done by University of Messina that's partner in TEMA. They have done federated learning using a number of heterogeneous nodes, for example, Raspberry Pi and cloud computers and so on. But we did not, we as Aristotle University of Thessaloniki did not enter into this research line.
Okay. A final question from my side. What do you think that it would be the domain of application that is highly touched by this kind of advances between all the domains you mentioned or all the domains out there?
You know, there are many cases where there is an urgent need for cooperation and a big issue regarding privacy. For example, let's suppose that we have a big problem with cancer images. We want to have better trained algorithms for lung cancer data. Various countries have such data. They don't want to share them, of course. And then the only way is to use such platform to train DNN models, for example, in a federated way. This is one possible application area. Another possible application area is in the case of natural disaster management. For example, you have an incident, you have the start of a fire, your systems are not that well trained. So instead of taking a decision right now, you can ask the inference results from other DNN agents that exist in other European countries that are also specific to natural disaster management. And then you can do collective inference, and hopefully you get better results.
Okay. Thanks a lot for your answers. I think we don't have any raised hands or questions in the chat, so maybe we can stop here.
If somebody wants to ask, a question, please do voice up and ask your question. There's no need to use chat. You can just ask the question.
Sure, go on and raise your hand or start talking. But I think that we are not having any. You have there the email of Professor Pitas for sending requests in the future also, and you have an additional website for all the material related to the talk. So I think that it was a wonderful talk this afternoon, and with lots of stuff to think about and to use in the research in the future.
Okay, thank you very much, everybody, for attending, and you, Enrique, for coordinating this lecture.
That was wonderful, wonderful. Please, you all keep tuned for the next lectures we are having. Bye bye. Have a nice afternoon.
Okay, bye.